Pleasure to have Professor Geoffrey Fox speaking with us today. We're going to talk about AI benchmarks and time series. I think many of you probably don't need introduction about Jeff, but let me still say a few words. For folks who don't know Jeff here, Jeff is a professor here at UVA and a very long and distinguished career in computer science, mathematics, and physics. And I wanted to at least point out a few important sort of facts. Jeff was a Wrangler in Cambridge, or Senior Wrangler. Jeff, correct me, but
yeah, that's correct. Senior Wrangler.
Senior Wrangler, right? Which is a very, very distinguished statement to make, because very few people are Senior Wranglers at Cambridge, and they've gone to become known mathematicians in many cases. And Jeff was at Caltech for a while. He was the chair of the physics/computation division. And had an opportunity to work with Feynman and guide his students who develop various techniques. He's done some remarkable work in HPC, physics, and software systems. So Jeff, over to you. Thanks a lot. He's been a mentor of sorts for us since the time he has been coming to Los Alamos, and for me personally. So I really appreciate, Jeff, all the mentorship you have given to this group.
Thank you. All right, let's get started. As we'll see, this talk is actually about earthquakes most of the time, and it's sort of slightly sad that after I announced this talk, we had the terrible events in Turkey. I'll mention that a little, not much. Okay, so we'll start with benchmarks. And I will just bring to your attention this activity called MLCommons, which is largely run by industry. And it's probably the best collaboration I've ever had with industry. In that they're very active, and they have 15 working group meetings a week in MLCommons. I certainly don't go. I used to go to more than I do. And it has 62 companies, not so many universities. They'd like to increase the number of universities, just 11, and a significant Department of Energy activity through the Office of Science Labs. And the estimate why somebody gave me was there's around 50 full-time equivalents from industry. We're essentially all making benchmarks, designing benchmarks and data sets and running them on big machines. And at the bottom right, it has the mission of MLCommons, which used to be called MLPerf, but MLPerf is the benchmark set and MLCommons is the organization. And it wants to accelerate machine learning innovation. And actually, it would be happy to receive ideas where it could contribute. If you look at the people who you see in those meetings, there are lots of HPC people. Obviously, this whole area of trying to make machine learning run fast enhances the number of HPC people you'll find. They basically do three things, which is sort of interesting: benchmarking, data sets, and best practices. They recently released a data set, an image data set, which tries to be very fair and diverse across areas and remove biases. It has a best practice activity where, for instance, we're working on trying to make fair data sets. It has also the benchmarking, which has all the models in it. So that's what the first part of this slide says. If you look at the benchmarks, they either measure performance, or in the case of the work I do, it measures scientific discovery. Obviously, you have to, the benchmarks include models. Every benchmark has a reference model. And although it's called MLPerf, it is really DLPerf, because essentially every benchmark is deep learning at the moment. We're trying to develop, or we have developed, an AI for science resource in MLCommons. And so that's the working group, which I set up almost 2.5 years ago now. We have completed 4 benchmarks, which are put around the bottom and the right side. One is satellite image processing. One is the one I'll explore more today, the earthquake time series predictor. Another is electron microscope data predicting material structure, space groups and things like that. And then another is in drug discovery. There is, as well as the science working group, a rather complementary and very active working group called the HPDC working group, which is run almost entirely by the Department of Energy. And it has 4 pretty interesting science benchmarks: cosmology simulations, weather prediction, energy and molecular science. That's Open Catalyst, and they're just adding OpenFold, which is an open version of the very famous AlphaFold, which was so successful at predicting protein structure from Google. I just finished with a few remarks on performance. So the recent interest in the chatbot, GPT chatbot, sort of puts in focus the importance of this plot here, which points out, this was originally shown in a talk I listened to by Rick Stevens from Argonne, and it shows there is, if you look at the number of flops needed to train a model, that number of flops has recently got extremely large. That's the sort of red items which are at the top of the graph. It is notable that there's very little academic contribution to those models. So
Jeff, can I ask a clarifying question for that slide? It's very telling. So just as an example, we can take any of them. AlphaZero, it says that in 2018,
it uses 5 times 10 to the 22 flops.
Right. And do we have something which shows how the next version of AlphaZero is doing it? But I'm sure the new versions like ChatGPT-3 is using much more. And so
well, GPT-3 is in 2020, and it is a little over 10 to the 23. GPT-3, if in the I have another plot which is in a different talk, but GPT-3, as in those plots, is not the largest system. I don't even know they know whether the latest, ChatGPT has how it was trained and whether. Right. But the largest, there are Google large language models which are much more intense than GPT-3. Also, there is an interesting development in that there are new models, so-called mixture of experts, which instead of having one giant model have up to 128 submodels, and they are much faster to train because you don't once you've decided which expert you're going to use, you're training you have a smaller network. Right. And I think there's going to be some development which will actually stop this rise being as dramatic as it is.
Right, because 10 to the 20 or e to the 24, the stunning number. I mean, this is not a sustainable number. And as you said, that's why academics have no role in this left, because you
that's
don't.
Right. You can't, academia, it's very hard to compete, period. And for these, it's impossible to compete. And of course, another important point is you might have to spend a lot more time actually refining the hyperparameters. At least in some of the networks, you can run up to 100 hyperparameter choices.
Right. I think a plot, Jeff, that has 3 axes. One is the amount of data that is being used to train, like ChatGPT-3. The flops that it is using and number of hyperparameters it has would be rather telling, because that's the way the complexity is going. All 3 numbers are increasing.
That's right.
Okay.
I mean, I don't know. Actually, we could even try to discuss this. If there's a large training set which we could somehow learn about epidemics from the papers on epidemics or something. Right. That could be an interesting project to do.
Thanks.
Well, here's a much more straightforward graph. It just says that from when MLPerf started, December 2018, until June of 22, performance increased a factor of 32. Which is obviously more, well, shown here, it's more than Moore's law, and Moore's law doesn't even exist, so it's slowed down. I mean, but of course, that partly is simply that they're just running much larger systems now. And that's, I think, shown on the next slide. Well, here's the remark here that if you look at MLCommons results, the largest systems are not the HPC supercomputers. At least not in the partitions used to do these benchmarks. The largest systems, which I have some measurements of in the next slide, involve 4,000 either GPUs or TPUs. It's interesting, MLCommons calls these clouds. We call anything a cloud which is not on premises. But obviously, anybody else would call them an HPC cluster because they have very high-speed networks, and NVIDIA owns Mellanox, which is the best HPC network provider, probably. So these are classic HPC systems. Though I focused on the training, they also have not only the data center networks, they have, for inference, they have data center, edge, mobile, and tiny, which are embedded systems. And they also do a lot of work on power as well as machine performance. This table points out something which is relevant for actually building systems. Namely, if you look at Frontier, which is the top 500 machine, it has nearly 40,000 GPUs. But you wouldn't use whereas you could use 40,000 GPUs on a large-scale simulation, you wouldn't use them on a single AI job, because if you look at these numbers here from the published MLCommons results, you can work out the classic efficiency, which is speed up over the number of accelerators. And for ResNet, the ResNet benchmark for GPUs, the NVIDIA machine, it was 0.16 on 4,000 GPUs. It happened to be a little better, 0.28 on TPUs, but still that's way less than 1. So you would probably never use 4,000 GPUs on those benchmarks. You'd rather run on, say, 512 GPUs, where the efficiency is probably around 50%, and run lots of hyperparameters. Use up your GPUs with hyperparameters. So this points out that the classic supercomputer is a little different from AI. It is a large collection of independent jobs, which are because the hyperparameters are largely independent, and any one job is going to use a modest portion of your exascale machine. Frontier is an exascale machine. On BERT, which is the large language model, that efficiency for both A100 and TPUs is less than 20%, 0.16 and 0.18. If you look at NVIDIA's newest systems, which they only have some small results up to 64 Hopper machines, that is substantially faster than the A100, factor of 2 to 3 faster. All right, so that's the end of that section of the talk. And now we'll come on to earthquakes. Yeah, our earthquake code is part of the benchmarks for MLCommons. So I've been trying to study earthquakes for 20, 25 years. And if you look at earthquakes, there are two rather different tasks. One is forecasting the occurrence of an earthquake, which is typically called earthquake science. And there's also what's called earthquake engineering, which is predicting the damage after the earthquake happens, or something which was done well in Southern California, but not so well in Turkey, building buildings which are not destroyed by earthquakes. And they're pretty different systems in that the earthquake engineering is complicated. There are lots of famous large supercomputer runs in that area, but you can actually solve a differential equation. I mean, you can calculate the earthquake waves. You know enough about the makeup of, say, the Los Angeles or Mexico City basins, or even the Turkish scenario, that you can actually predict the motion of the waves. And so given an earthquake occurs, you can calculate the consequences straightforwardly. So that I would call as theory-driven. However, it is not possible to easily predict the occurrence of an earthquake, because it comes from these earthquake faults moving, and they slip, and it is impossible to predict that slip because you basically don't have the boundary conditions, because the plates are underground, the friction laws are not known in detail, and you don't even know enough about the data. And further, this is a phase transition, which is particularly hard to predict. So in the language of machine learning, this problem has lots of hidden variables, those fault parameters. And so the only chance of being able to predict earthquakes is actually sort of the classic of data-driven science, it is to look at other data and see if this other data can tell you about the hidden variables. And then it also, if you have other data you can observe other than the actual quake, you can use this other data to predict the quake.
Jeff, I have a question.
Yes.
So do most state-of-the-art systems take into account the city structure and such? That would be the third level, right? This one is more understanding the physics of the wave propagation.
I think they put in the city structure. Yes, you can do
Okay.
that, because that's again known. That's
Right.
known data.
Right. So when we were at Los Alamos, people had come, after the earthquake in California, they were trying to compute, but insurance companies would be interested in the topical area because they're trying to insure buildings at various.
That's right. But what the earthquake science will tell you is which regions of Southern California or the world are more likely to have an earthquake in the next few years.
Right.
As the large ones are quite uncommon, fortunately,
Yeah.
it's not realistic. When you have a Poisson process with a period of 25 years, you're not going to be predicting an earthquake in the next 2 weeks. You're going to be predicting in the next few years.
Okay, thanks.
Jeff, can I also ask a question here? We're thinking data-driven, and I can see sensors and things like that are all sorts of types of information that might come in, getting dog barks and stuff. But also, are you thinking about computational model output as well as something that might be part of this data-driven process?
Well, people have earthquake simulations, but they can just tell you what an earthquake looks like. They can't tell you about a real earthquake because you don't have the correct boundary conditions in those models. There was this famous Japanese supercomputer called the Earth Simulator, which was partly motivated by a horrible earthquake in Japan. And it built wonderful finite element solvers, but it didn't actually predict any earthquakes at all, because it couldn't do. I mean, that was actually, I think, known when they built the machine. They used the earthquake to justify it, but the earthquake science problem is not soluble with a large simulation at the moment. There may be some clever new development, but at the moment it's not soluble.
All right, great, thanks.
All right. These are just plots of the Southern California 4 by 6 degree region centered on Southern California. And the top left is the magnitude greater than 0, and the bottom right is the magnitude greater than 4.5. And that just says there's a lot of small earthquakes. And we're going to see if the small earthquakes can predict the large earthquakes. Here's a paper we recently wrote with John Randall. John did most of the work. It sort of explained the essential reason why this might work. Namely, there was a famous paper which pointed out that the sequence of earthquakes in Southern California is Poisson. And so that doesn't sound very promising, because if it's Poisson, there's not much you can do except determine the period. However, there are other things which are Poisson. You have a Poisson distribution of earthquakes magnitude greater than 6. You also have a Poisson distribution for earthquakes of smaller magnitude, and you're going to see a lot more of those. So we showed there was a clear correlation between the number of earthquakes greater than, well, we chose 3.9, let's say greater than 3, and that had some hints as to the occurrence of the larger earthquakes. So this again comes back to this hidden variable issue. Most things are Poisson, but if you can observe a common Poisson distribution, you might be able to predict the uncommon one. And that's sort of what we're trying to do here. And I'll show some quantitative pictures of that later on. Here's just a slide I did given the Turkey problem, to the earthquake in Turkey. So we're trying to predict which places have the most likelihood of a large earthquake in the next few years. However, if an earthquake occurs, they do try to give warnings, and certainly in Southern California, that's very well developed. And that uses the fact that the different waves have different velocity, and the most damaging S wave is slower than the P wave, and you can detect the P wave first and use that to tell people there's an S wave coming along, which will give great damage. So that's called shake alert, but that's only going to give you a few seconds of a warning. And it is possibly interesting to see if one can do better than that, but that's not what we're doing. Although the Turkish event points out how important that would be. Now, here is just a contrast of things people here know more than me, that is studying pandemics and things. So if you, the earthquake problem is that the physics is impossible to understand because we don't have the boundary conditions. If you look at pandemics, then there are all sorts of other issues due to the fact that you're interfering with the system due to various external forces, which are not physics, like people. Well, they're sort of not physics. And if I gave an example, just I happen to remember that if you look at the number of flu cases, it's pretty small in 2021 because of the COVID precautions stop people spreading flu. And it's quite hard, therefore, to hope that to train a good network which puts all these external forces which are affecting the answer. But in earthquakes, we don't have any such external forces. As far as I know, everything is physics related. It's just that the physics is so sensitive to the unknown details of the boundary conditions. All right, so here's a very mundane slide, which points out that we're using the Nash-Sutcliffe efficiency, which is defined like this. It's the ratio of the standard deviation of about the mean to the standard deviation between the observable and the data. This comes from actually the field of hydrology. If the Nash-Sutcliffe efficiency is 1, you have described the data perfectly. If it is minus infinity, it's a disaster. You can get 0 by predicting the result to be the mean over time. So the results are presented in what is called the normalized Nash-Sutcliffe efficiency, which is maps minus infinity to 1 to 0 to 1. It's 1 over 2 minus the Nash-Sutcliffe efficiency. There is no standard in this field for how you measure success. Here's another pretty important trivial point, which is, what do you measure? And we use 2 types of measures. And we'll come back to this a little later on. Obviously, if you listen to earthquake news, they always talk about magnitudes. Well, magnitudes are the log of the energy. And it's sort of important to decide what you want to use, because if we think about a neural net is going to come along with weight matrices and take inputs and multiply them by matrices. And it's a bit different to multiply the log of the energy versus multiplying the energy, because physics is energy, and energy is additive. I mean, you add energy. So it's a little worrisome to me that we should present results as magnitudes, but we are going to use magnitudes, because if you use, we'll see, if you use energy or even a square root or fourth root of energy, you have such a wide variation in the ratio of the maximum to the mean that it is not possible to get a good description with, at least with current neural nets, because current neural nets have all the action around unity. And if you have huge variations of your input data, it's difficult to see how activation functions are going to work properly. You can't really add magnitudes. So for the input data, where we take measured events, we always convert the events into energy, add the energy up in the bin, and calculate the log of that summed energy. And that is what we use, which is, I call it log, it's called log energy, but it's effectively magnitude, but it could be summed over events. However, we also look at multiplicities, and multiplicities are just counted. So if we look at the number of earthquakes greater than 3.29, we just add up as a number. But the results are very sensitive to how you do this. Another minor technical point is just get a clean system. We take this region of 4 degrees by 6 degrees, and we divide it into by 0.1 pixels. That's also slightly arbitrary, but it's around the right value. It's about the size of a uncertainty in the earthquake position. And we have therefore 2,400 of these points, And the points are not strongly related, except maybe by the faults that go through them. Whereas for the earthquake engineering, you're going to do wave equations, which will nicely have locality and spread from the center. The earthquake itself doesn't have such clear spatial correlations. Anyway, of these 2,400 regions, we just used 500, which were the 500 with the greatest activity. So that was just a choice to reduce the size, the data set size, and have things which focused on having significant data. So the data comes from USGS. The data is events. You then bin the data into a suitable time interval, and the time interval we use is either 2 weeks or 4 weeks. The data here is 2 weeks. So we bin the data, we calculate this log energy, we also calculate the multiplicity in each of those bins, which are binned by the spatial position and the 2 week interval. Our input data is every 2 weeks, but we're going to be predicting multi-years into the future. So I'll come back to how to do that. There is no missing input data, there is missing predicted data, but that's trivial. You just drop predicted data from the loss function. So here is a sort of standard terminology from the literature. We have observed inputs. Those are things like the magnitude and the depth of the earthquake. For COVID, those would be the infections and the fatalities, and vaccination rate and social distancing. We also take these multiplicities as observed inputs. The targets are what we're trying to predict, whereas the data, input data is naturally every 2 weeks. Our targets were going to be the data averaged over long time periods. So we have multiple targets because we're going to predict multiple time intervals from 2 weeks up to 4 years. So we calculate those targets. And again, that's something which is, again, not very well, as far as I can see, studied in the literature, which targets you should use. Most of the known examples, like electricity load and things like that, everything is just the data for the particular time intervals that you've chosen. There's an interesting concept which I first learned about from a paper by Google called known inputs. These are things which are just known as a function of time. There are static features in the case of COVID, say, it could be number of hospital beds would be a static variable. In the case of earthquake, the static variables are the fault locations. If you have a particular region that's in a particular fault, that's a static variable, which fault it's associated with. In some of these commercial papers you read, they will use things like a static variable, which is the signature of a holiday. You'll have a variable which says, this day is a holiday, or this day is a weekend. And I'll come back to mathematical known input. Things like if something is a holiday, that is a known input because it's known for the future and the past. So this just illustrates, here's say COVID data summed over all the counties. If I happen to use this program to look at COVID data, which I didn't in detail, well-known has a striking weekly structure. And in fitting this data, we all feed in cos theta and sine theta, where theta varies from 0 to 2 pi over a 1 week period. That I call them. We do, if you think about all these neural nets, you can feed in known inputs, which can actually be your theoretical prediction. Or if you like, you can just feed in standard expansion functions. I use effectively Fourier transform and Legendre polynomials. Here is the COVID data. Student Eric A is working on that with me. And here you have annual variation. So you feed in as a mathematical known input, cos theta, sine theta with an annual, with a period of 1 year. So here is technically what we'll use. We have the targets of the inputs for the log energies for 2 weeks up to 208 weeks. And the mathematical functions are either Legendre polynomials or cosines. And we're going to have 3 different models, the Google Temporal Fusion Transformer, a standard LSTM, and a transformer I developed, which I happen to call the science transformer. Here's a little comment on predicting longer time intervals. because in some of the problems, like predicting electrical load or predicting sales, which is what the temporal fusion transformer uses in its early papers, it predicts, say, a year in advance when it has, say, daily data or weekly data. As I said, it has weekly data and wants to predict a year in advance. It would just predict 52 time periods of length a week into the future and add up those time periods to get the yearly prediction. So the TFT is focused on a single time period, and it just predicts multiples of those time periods into the future. That does not work at all for earthquakes because, unfortunately, because of this log, because we're looking at the log of the energy, log and averaging does not commute. So you cannot take the predicted magnitudes for the next 52, well, let's say the next 52 two-week intervals, so that's the next 2 years. If you did that, you can't predict the earthquake because you need the maximum, and that doesn't work. So you have to explicitly predict the long time prediction. So I don't know what's normal in there. I've not seen this discussed in any great detail for other problems, but we just fed in the predicted, well, actually it's up to 208 because we did 4 years, not 2 years. It should say 208 delta T here. So here's just a simple discussion of the various methods. The LSTM is very straightforward. It just has an input encoder, a couple of LSTM layers, an output decoder, and that's straightforward. The science transformer starts off with a basic set of transformers. I mean, the idea of a transformer is to look at patterns. And I've told you there is a pattern. The pattern is that there are small earthquakes ahead of time of the big earthquakes. And so it's reasonable to hope that the transformer could detect that. As we're trying to predict numbers, which is magnitudes, we start off with a transformer and then add an LSTM layer for the decoder. TFT is a very complicated architecture, which I recommend you study. And it is very successful, at least in things like predicting electrical load, where you have, well, I think that's mainly hourly data and trying to predict days into the advance. And so it's clearly focusing on problems where you have data at one time interval, you want data at another time interval, but the answer you want is the sum of the answer over the smaller time intervals, something which is not true for earthquakes.
Jeff, can I ask a question? This is Chris. So as far as these time intervals are concerned, suppose that you have had an earthquake and what you're trying to predict then are aftershocks. So you have the given event that's Poisson, and on the other hand, the Poisson distribution is resolved. I mean, you have one. Now you have these other timescale Poissons. Can you rapidly then calculate?
Actually, we're not trying to predict that, but that is not so difficult. Large earthquakes are followed by lots of small earthquakes. Unfortunately, large earthquakes are not preceded by lots of small earthquakes.
Right. So, but I'm saying if you look at the use of these multi-scale calculations, if you look at the use of them in decision problems, given that one has occurred, whether you predicted it or not, I mean, it would be very useful for this other piece. And I just wonder how that goes.
That is something you can do. We did not focus on that in this problem. We were mainly focused on trying to do the long time scale prediction of a large earthquake, because that's sort of what affects whether the insurance rates and things like that.
So the decision class determine, I guess this is my point, is if your decision class is response. So the decision structure, as usual, I guess, but anyway, just to make the point, drives the representation form, yes, even when we're talking about this level of prediction.
I think actually Turkish earthquake suggested to me we should relook at some of these forecasting something different, something that would help people after it occurs, but we didn't do that here. What all this plot shows is that the temporal fusion transformer has lots of parameters, and so it was very easy to get overfitting where your training is much bigger than your validation, but we stop the fits when the validation starts increasing. There's not so much problem with the recurrent neural net. The validation still goes down a little after it crosses with training, and we just stop when the validation gets too big, starts increasing. Here are some results. So you get results like this. So this is from 1955 to 2020. This is 2-week data, and this is just the log energy summed over 2 weeks. And the training data is on the left, and the validation data is on the right. And you get reasonable predictions. This is, the first was the LSTM, next is the transformer. This must be the TFT, the temporal fusion. The TFT, because it has these lots of extra parameters in it, it tends to fit and will probably overfit the data better. It doesn't actually give better validation results, but it can give better training results. But that's probably artificial. 2 weeks, 6 months. Here we plot the data every 2 weeks. For each 2-week time period of 2 weeks, we just look 6 months ahead and ask what the log energy is for the following 6 months. And so this is predicting 6 months in advance. And again, you have 3 plots, which we will actually find so here you see the TFT is getting far better training results, but the validation is not nearly as good. 4 years, here's our final plot here. So this is probably the most important prediction. And also I should point out, as it needs some time to learn the result, the prediction at early times is not as good as the prediction at late times. So as we're gathering more data, we are actually predicting the results better. So here's 4 years from the transformer. And here, so that first one was LSTM, the second one is transformer. We did not have a TFT for 4 years because the model didn't easily predict for it. It needed too large a model to predict 4 years in advance. Now here is the so-called Nash-Sutcliffe efficiency. Remember, 0.5 is you predicted equal to the mean. And so we are finding for all these intervals here from 2 weeks to 208 weeks, we're getting results which are for the training of somewhat over 0.9, and for the validation, it's 0.81 for, in this case, for 4 years, and 1 year is the best at around 0.8, nearly 0.9. All right, here we come back to this physics idea that there is some correlation between the number of small earthquakes, which are, well, let's call them medium-sized earthquakes, the number of earthquakes greater than 3.29 and the big earthquakes. And you effectively define a state which is just a sum over 3 years, the number of earthquakes greater than 3.29, an exponential moving average. And when you find that what happens is it increases, levels off, and then there's an earthquake. And so this is saying that this number of small earthquakes actually decreases with time. And that decrease is a signature that is likely to be a big earthquake. This has nothing to do with the deep learning network, but it suggests there is structure there for the deep learning network to learn. And here's the same result for Turkey. And these results for Turkey do not look quite the same as Southern California, which probably reflects the low quality of the Turkish data. The earthquake which just occurred, the predicted probability of an earthquake was 47%, which may be okay, but it's no, it doesn't look quite the same. The pictures look different from those in Southern California, so we need more work here. So here is actually the more precise version of this with deep learning. So effectively, that physics model tells you what to look at, which is the 3-year or around 3-year average of the total number of modest-sized earthquakes. And I started with a LSTM, which had a 0.93 training and a 0.8 validation. When I added in these physics observables, I got a much better answer. The 0.93 went to 0.95, and 0.8 went to 0.87 for the validation set. So actually, I took 9 different. I mean, the physics has some parameters in it, which mean it's not quite certain which particular physics observable to look at. I just added in 9 extra physics observables. One advantage of deep learning is you can have any number. It doesn't matter how many observables you have; it still converges and fits throughout the same performance. So if we just if we just use raw multiplicity and not this smoothed out version, which the physics suggests, that's this thing at the bottom, and then we just use 9, and then we took the best of those 9, and that actually gave currently the best answer we've ever got. So this sort of is interesting. It says that we can feed in the physics prediction as observables. Oh, here's actually the picture of the 4-year prediction. This is without the physics observable, and this is with the physics observable. In the old days, we used to start with, when I used to do physics models at Caltech, as Madhav kindly noted, I worked with Feynman building physics models for parton high energy collisions. We took the theory models and fitted it with the data. Then if you read standard classic deep learning, you will do everything data-driven. But somehow what we can do now is mix them up together. We can actually take the theory and feed it in as a known input into the model, so that you can actually force the time. I showed you can do that for the time dependence. You can do that for these physics observables. So I think that's one interesting lesson from this analysis. Well, I want to come back near the end on this choice of variables. This is a general problem in these models. They're very sensitive to things like mean square error versus mean absolute error. Like I presented answers with mean square error. If you use mean absolute error, it doesn't work, at least not for the LSTM. It gives bad answers. And these are all due to the fact that if you change either the loss function or the particular observable you use, it makes huge impact on the relative weight of different data points in the loss. So if you have mean square error, large observables are weighted more than in the mean absolute error. And if you look either at earthquake data or COVID data or hydrology data, there are huge variations in the size of these observables. And I say affects the loss function, also affects the action of the neural net, because the activation layer will not find it easy to act in the same fashion independent of the size of the observable. And I've already pointed out, as far as I know, there is no rules. Namely, if you have an observable x sub I, you can replace x sub I by any function f of x sub I probably you want f of x to be monotonically increasing, and square root of x, log of x, they're all monotonically increasing. So even if the physics says energy is most important, you can use square root of energy, which happens to be the strain, or the natural observable, which is magnitude. And it's not so obvious what the right thing to do is. I say, let me just look at this next plot. This plot points out the huge difference between these choices. This yellow curve here with minor bumps is magnitude in 2-week intervals for this data. If I use the square root of energy, then you can see a big peak here. And these peaks give lots of trouble. It's shown here. This is just the standard LSTM using magnitude. If I do the same LSTM using, here is the 4th root of energy, it's not even as extreme as the square root, the fit is terrible. That's because it finds it very difficult to predict the peaks and get the smaller values correct. So, as far as I can see, there is another comment I could do here, namely, there's the mean over maximum. The mean over the maximum is 10 to the minus 5. One interesting observable is the square root of x, because if you have things like COVID with observing events, if you feed in square root of the events, then you will find that then your loss function, standard deep learning loss function, is actually chi-squared. N has error square root of n for Poisson distribution, and square root of n has error order 1. So there is some reason to actually look at these functions, but you can just make the general comment that there's an extreme dependence on how you treat any numeric data with a wide range of values. So that's just a lesson, and given the time, I'll stop at this point here. I have a summary here. I tried to note there are some areas where there's not a lot of consensus as the best practice, how we do these multiple time intervals. The TFT claimed there was some problem with predicting multivariate, and but I don't understand. The role of known inputs is pretty important. Measuring success is not again an agreement. I use the Nash-Sutcliffe efficiency. There is some uncertainty about test and validation, whether you use spatial or temporal decomposition. For earthquakes, the role of the faults is not clear, and the variables to use is also not clear. So there are plenty of uncertainties here, and so I'll leave it at that. I say, well, next step, I think, is that we're going to try to look at Turkey, and also we're working on improving the program to basically make it describe the world's data, which exists in many regions, northern as well as Southern California. There's very good data in Japan and Taiwan and places like that. Thank you.
Thanks, Jeff.
Yeah, thank you, Geoffrey, for your talk. If there are any questions, you can go ahead and ask them either in the chat or on mute.
Maybe I'll ask one question to start off, Gunda. Jeff, of course, the earthquake part is so important right now, given the events in the last few days, but would you be able to pull out basic ideas that we could potentially apply in our epidemic setting? There are a couple of them that you pointed out, I could note, but that might be worth thinking about, from the perspective of our expeditions project.
Yeah, well, obviously lots of people have applied these methods to pandemic data. I don't know that that's usually successful, partly because of the sensitivity to the data. The results are somehow not easy to learn, because you have to learn what particular precautions people are taking at the moment. So you have to feed in that correctly.
Right.
But I would assume these issues about predicting into the future would have some, which are very, very important for earthquakes, are also relevant for COVID.
If we want to just predict whether a pandemic will happen a year from now, which is actually of interest to some people.
Yeah, well, that of course is similar to the earthquake problem. Earthquake is effectively trying to predict that. It's doing it in a slightly quantitative fashion by the probability of a large quake, but it is effectively asking, yes, no, is there an earthquake?
Right. Something that I've been thinking about. There, perhaps some of the techniques that you have would be useful. I don't quite know. Of course, the human part still continues to play a role, but perhaps if you go so far ahead, and the point is, human behavior certainly plays a big role in all the evolution there. But perhaps if you go way ahead in time, maybe that part becomes somewhat smaller in terms of doing such a prediction. Is what I was thinking.
Well, it'd be good to study it. If you'd like to do that, I said we can try to do that.
Yeah. Okay. Thanks.
Jeff, can I? I don't know if I think this is a question. I hope it's a question, but it has to do with this notion of prediction and how far ahead the prediction is useful. And I guess the other thing that I mentioned earlier, the decision problem. So I'm going to just postulate a decision problem just to make a point. If the goal of the prediction and stuff is to give warnings to the population that are actionable over time period, like evacuate, leave this particular area, prepare for something, expect something, right? Like that is to say, not on such a long time scale as just adjusting your insurance rates, but it's a different management problem. They're both management problems and they both involve prediction, but they're somewhat different. Then the predictions are successions of short-term predictions that don't have to, they can, as long as they're pretty good up to the next round of sampling, which could be fairly short, seismic sampling or whatever, and you're filtering essentially these time series. And if you get a pretty good hit, then it's some fairly short period of time in advance, even hours or something, but useful for management. Then the notion of what's a valuable prediction and the constraints on it and all the things you have to do, its value, are somewhat different than if you need some much more sort of aggregate level information about sort of in an area, how many earthquakes of what severity and in what sort of, infrastructure locations and stuff that would be made for purposes of insurance or infrastructure building codes or something. It just seems to me that this sort of thing can be made useful in this really interesting and important management way that's also important to things like epidemics, which, because of, just as you said, because they're coupled with behavior, maybe their prediction windows are different, is shaped differently. But nevertheless, over these shorter time intervals, sort of filtering time intervals, they can both be really useful. And the adaptation of these things to those kinds of problems is really interesting to me. I just wonder how you see that. I
think I came to the same conclusion just looking at the sad Turkey events, where clearly they suffered from not getting a good warning out. So that emphasized to me the importance of the warning. In the case of Southern California, that warning is so well established, and and the buildings are built so much better. It's not quite as serious. But for other parts of the world, I suspect the warning is the most serious. The near-term warning. Please get into a safe place. That warning is obviously very important. So I agree with you. I think I think we should study that. I've started talking to John Rundle about that issue.
Okay, any last questions before we close for today? If not, then I just want to say thank you to Geoffrey again for speaking today for the seminar series. And thanks for joining us today.
Thank you.
Thank you very much, Jeff.
Bye, everyone.